So now we can proceed to linear regression and logistic regression. So linear regression is one of the aim of linear regression is to model a continuous variable y as a mathematical function of x, so that we can use the regression model to predict the y when only the x is known. So the function normally looks like this, like beta 1 plus beta 2x plus epsilon, which is an arrow. And beta 2 is a slope, beta 1 is interception. So here is a brief example. So if we have a data like shown above, below, we can first do a scatter plot. So the scatter plot can help visualize any linear relationship between the dependent variable, which is the response, and the independent variable, which is the predictor, so that we can see whether they have a linear relationship. We can see from this graph, without modeling anything, we can already see like these two variable has a pretty much fair good linear relationship. So now we proceed and we want to check the correlation. So correlation is a statistical measure that suggests the level of linear dependence between two variables. So correlation can take value between -1 to 1. If we observe for every instance where speed increase, the distance also increase along with it, then we'll see there is a high positive correlation between them. Therefore, the correlation between them will be closer to 1. In the opposite, if we see something like a -1 for correlation, we'll see a negatively linear correlation. If you see something like a value like 0, then this kind of suggests that there is no linear correlations between these two variables. And we'll consider correlation negative 0.2 to positive 0.2 low correlation. So now we want to build a linear models. Now that we can see there's a linear correlation, a linear relationship between these two variables from both the scatter and the coefficient plot, we use this LM to fit a linear model between these two variables. So where we need two input, the first one is the formula and the second one is the data. So in this case, the speed is going to be the x, and the distance is going to be the y. So after we build this model, we establish a relationship between the predictors and the response in the form of a mathematical formula for distance. And we can see like the interception is negative 17.5, and the slope is 3.9. However, the standard linear model performs poorly in the situation where you have a large multivariate data set containing a number of variables prior to the number of samples, which means you have a really small sample size. So a better alternative is the panelized regression, allowing to create a linear regression model that is panelized for having too many variables in the models. By adding a constraint in this equation. So here I'm showing the ridge, lasso, and the elastic net as the penalties. So ridge regression shrink the regression coefficient so that the variables with minor contribution to the outcome have their coefficients close to 0. The shrinkage of the coefficient is achieved by panelizing the regression model with a penalty term called the L2 norm, which is the sum of the square coefficient. The amount of penalty can be fine-tuned using a constant called lambda, which is right here. When lambda equals to 0, the penalty term has no effect, and ridge regression will produce the classical least square coefficient, which is the classic linear regression. However, when lambda increases to infinity, the impact of the shrinkage penalty grows, and the ridge regression coefficient will get close to 0. And now we can talk about the Lasso regression. The Lasso stands for least absolute shrinkage and selection operator. So it shrinks the regression coefficient towards 0 by penalizing the regression model with a penalty term called L1 norm, which is sum of the absolute coefficient. In the case of Lasso regression, the penalty has the effect of forcing some of the coefficient estimates with a minor contribution to the model to be exactly equal to 0, whereas the ridge can only make it close to 0. So yeah, this is the difference. And this means that Lasso can be also seen as the alternative to the subset selection method for the performing variable. So yeah, and the same as ridge, Lasso also has this lambda term. When lambda is close to infinity, some of this non-important coefficient is going to go to 0, and in that way we achieve the variable selection purpose. And ElasticNet produce a regression model that is penalized with both L1 and L2 norm. The consequences of this is to effectively shrink coefficients and to set some coefficient to 0 because it has both the ridge and the Lasso property to it. And then how should we pick for lambda? We use cross validation to pick for lambda. We pick a lambda that gives us a lower test error. So now we can talk about what is k-fold cross validation. So in the k-fold cross validation, the original sample is randomly partitioned into k equal sized samples. Of the k samples, a single samples subsample is retained as validation data for testing, and the remaining subsamples are used for training. The cross validation process is then repeated and k times, which each of the k samples used exactly once as the validation data. Then you average the accuracy of the validation accuracy to get the final accuracy, and from there, with different value of input, you will know which of the from this accuracy, with different value of input, you will know which value is the best. And now we're ready for an example of this this regression models. So let's use the Boston data for predicting the median house value in Boston suburbs based on the multiple predictor variables. So first, we randomly split the data into training set, which is 80%, and test set with 20%. And then we specify lambda into a sequence from -3 to 3 with 100 of them value inside. And then we use the ridge regression. We set alpha equal to 0, so it's a ridge regression in that way. And we use cross validation of 10-fold cross validation to find the best lambda. And this is and then we get the coefficient of each of the variables from this linear model. And then we predict, we use the ridge model to predict the outcomes of the test data sets. And we compare the actual value and the test and the prediction. We got a square R square of 0.76. And then to compare with the Lasso, now we put alpha equal to 1 and still use the cross validation of 10-fold to find the best lambda. And in this way, after we find this coefficient and stuff, we see R square of 0.76, which is very similar to the previous ridge only one. And Now we want to look into both. So we use the elastic one. Without now we don't specify a lambda. So in that way, this cross validation is going to we don't specify the lambda. And this cross validation is going to find the best value for us. So after we did this prediction, we got like very similar 0.76. So we can see from and then we did a comparison between these three models, and we can see from here, yeah, they are pretty similar to each other. Yeah, they're like pretty similar to each other. And the best model is defined as the one that has the minimized the prediction error, which actually I think they're pretty similar. So yeah, and it doesn't matter.